How's the torque and joints world? You going okay? It's a weird assignment, I get that. But hopefully it helps you think practically a little bit.
Is the needle like that on the bottom?
This is entirely a needleless turntable. Probably used to be one, but for what I use it for, I don't need a needle. By the way, yeah, this is, you know, those small records, they're called, or no, the full-size records are called 33s, yeah. And the small records are called 45s.
Yeah.
Why 45 and 33? What's that number mean?
The RPM.
That's RPM, yeah? Or there's 78s if you're really crazy.
Yeah, just like nothing.
What are we talking about? 33, 45, 78.
Record.
In records, what does that number mean, though?
RPM.
Well, the letters are RPM.
Rotations per minute.
Rotations per minute. So you whip out your favorite record. By the way, your favorite record on vinyl now is? I have no idea. He's thinking.
Everything will be all right.
Just use your imagination, and I don't know what it is, but there's your favorite record, and more than likely your favorite record. If it's a single, it's a 45, right? Yeah, and what's 45 again?
Rotations per minute.
RPM. But yeah, that means rotations. If we write it in fraction life like we do in the rest of sciencey things, we'd say 45 rotations per minute. Okay, my question, what the heck is that measuring?
How many rotations it makes in a minute?
I mean, I guess so. It's good.
Yeah. It's really
How many
self-explanatory.
rotations? I guess it's pretty straight up. Now, wait a minute. If you think about that groove, because records are groovy, right? If you think about that groove, the groove behaves the same as you go across the different parts of the record, like from the middle to the outside. The thing goes at a constant rotation. It's kind of weird to think about when the needle is dragging along in the groove out here versus in here. Is the needle covering the same amount of groove per second?
No.
Wow. So how does a record get groovier? Wow, I feel like there's a stupid joke here we could work out. I guess it gets less groovy as you go because it goes to less whatever. All right. So what I want to think with you about today for a few minutes is how we can, yeah, we're gonna start spinning records. I'm a DJ on the back. I do play in a couple of bands now.
You should put that on the turntable.
Yes. How do you feel better?
Nice.
Oh. So what I want you to think about for a couple minutes is how we can translate, I shouldn't use that word, but I did, our world of kinematics that we've been living in together for quite some time into a world that goes in circles. Now, we studied circular motion a while ago, and we studied a point going in a circle, and we got to the point where we recognized pretty well, hey, to go in a circle, it takes a force towards the center. But then we came along and said, well, what if stuff has shapes? Oh no, now they know I put their shapes in the trash can. Oh well. At least I put them in the recycling. Then we got to thinking about, well, maybe shapes matter. And then we did stupid human tricks. Well, now what I want to help you think about, pardon me, very smart human tricks. What I want to ask you to think about is how can we talk about motion of a solid object that's moving in circular motion. We need new language. Because if we use velocity, for example, to describe this thing going in a circle and talk about how fast it's going, well, do you mean the outside edge? Or do you mean 5 centimeters off the middle? Does it matter? If you think about the outside versus halfway in, are they going at the same speed? Well, if by speed you're talking of meters per second, the short answer is, no, they're not. Where's the speed greater, outside or halfway in? Outside. So all of a sudden, if we talk about speed, if we're talking about a solid object rotating, we got ourselves a little bit of a conundrum because speed is not uniform. It depends rather on the what? Spin on. Even if this thing is turning at a constant rate, the linear speed depends on the radius. Depends on the radius. So here's a thought. I want to think with you about wheels, circles, if you will, and the way that we define a bunch of quantities. And as you're well aware, if you take a circle, we can measure lots of things about circles. One of the fairly easy things to measure about a circle. What distance might be real easy to measure about a circle? Some of the things you can measure might include
Yeah.
diameter, circumference, radius.
Here we
What?
go.
Do you want to record this?
I am and I did, and thank you for asking.
Yes.
Good call, appreciate it.
Here we go.
So diameter, circumference, radius are all linear measurements you could make. From those, you could calculate areas and other things. Yeah, those are useful. Specifically, if we draw some pictures, I'm not going to tell you, you don't already know what these are, but we're going to stick to that one as being pretty useful. Of course, that one is named radius. We're going to use the term radius a bunch. Here's a weird thought. If you take a circle and you measure, let's see, I won't get as fancy to poke a hole in this. If you measure the distance to the outside of the circle, of course, what's that? That's called the radius. Oh, all the scissors are in the lab. There we go. So this is a really high-tech representation of the radius, yes? How does the radius have anything to do with what we can measure now? Well, just a reminder from Mathland, if I start somewhere on the circle, there's a red mark here, but I'm going to make it green because there's another mark in another place. And I start going along here with my radius. Hey, there's about one radius along. Yeah. Hey, there's about 2 radii along. I can do this for a while. All right, I can do this for a while. 3, 4. How long can I do this for?
A little over
5, 6. I end up just a smidge over 6 times around. That's weird. Yeah, there's some interesting ratios that we figured out a long time ago. Thank you, Greeks. And of course, the connection between a radius and all the way around is a very familiar number, you know, called 2 pi.
Pi does everything in circles.
2 pi.
That's why we have radians.
But if you start at somewhere, like my green mark, and you go around the circle and make another mark, we can also think of that slice of the circle, yes? And if you think of that amount of angle, the angle made by one radius spread along the circumference, what do we call that angle? That's defined as 1 radian. 1 radian. Yes. So a radian is a radius laid down along the edge of the circle. It's not that you don't know that. It's not that you don't have experience with that, but I want to remind you that. So if you take a radius and you start laying it down around the outside of the circle, this is so much harder than drawing on the board for real. You get 1 radius of arc length, yes? And if you go to that end of that radius of arc length, and then we define, right again, this angle, that angle, we call what? That's defined as 1 radian, yes? Because if you go all the way around the circle, 2 pi radians, yes, is the same as some other names you have for it. 1 circumference, also the same as, what else do you know?
360.
360 degrees. We got a bunch of names for that. Yeah, there's radians and radians, and there's a bunch of crazy ones. But, okay, so here's a thought. If you want to think about angle, we could define the angle, as long as we're in radians, as, hey, the distance you go around the circle divided by the radius. How many radii is it along the circumference? And that's our definition of what we mean by angle.
Magical thing that is between that circle.
Check this. So again, what's theta? Well, it's distance over radius, yeah? the distance around a circumference over radius. So if we write it another way, we can show that distance is just the product of radius. In this work that we do, you suddenly want to get your calculator out of degrees mode and put it in radians. Up until now, all the work we've done, we've had your calculator in degree mode. Here we're going to think about radians because it makes it easier. Now I got a question. I want you to think with me for just a couple minutes, because that's what we have, about rotational land. Yes, I did make up that name. And linear land. We've been living in linear land, but let's take a walk to rotational land. In linear land, we think about distances. In angular or rotational land, we think about angles. But you also know that we can look about the rate at which we go through a distance, yes? Hey, what do we call that? The rate at which we go through distance over time, what's that called? Oh, that's speed. Okay, that's velocity, right? So we know in linear land, we have this pretty comfortable concept called velocity. Hey, take a look on the right. What do we have over here that works like velocity? Well, same concept, but instead of distance over time, it's angle over time. G, what do you suppose we call it? Well, this would be called angle. But if we take angle over time, we call it angular, what? Velocity. In walks a new letter, omega. Greek letter omega looks like a curly W, but it's omega. And in order to put an equal sign there, I still need the R, yes? Omega represents the 45 on the record player. 45 RPM, that's a measure of angular velocity. Does it matter what the radius is? Not a darn bit. Of course, if you want to know the linear velocity, no problem. We can switch back and forth from one to the other. Any chance we could take another step? I feel like there's yet another idea in physics we've used a lot. I feel like we've had to think about the rate of change of velocity once in a while, yes? Well, that's probably the rate of change of our omega, yes? Anybody happen to have a name for the rate of change of velocity? I feel like we're pretty familiar with that one. Over on the other side, what have we got? Omega over t. Angular velocity over time. Give it a name.
Acceleration.
Angular acceleration. I need just a hair more space on my screen that I don't have. I'm going to squeeze, and I'm going to throw in an alpha. Actually, I'm going to throw it over here because alpha is the letter that we use to represent angular acceleration. And conveniently, alpha multiplied by radius, of course, gives us tangential acceleration. So all the things we've been working with over here, linear land, still work great over here. We just have new names for them. Instead of talking distance, we talk angle. Instead of talking velocity, we talk angular velocity, omega. And instead of talking acceleration, we think angular acceleration, alpha. How we doing? I won't go far with this part, and I'll post what I'm doing. But I bet you're familiar with this. df is di plus vit plus 1/2 at squared. That's the first physics tattoo you got, right? Oh yeah, once upon a time, those are kinematics equations. What if we rewrite this? Work with me. Theta final, right? Theta initial, what am I doing? I'm writing exactly the same equation, but what am I swapping out? Bless you. I'm swapping out linear land for rotational land. Here's the cool thing. As soon as you recognize the three letters, theta, omega, alpha, this is exactly nothing new. Could you take all three of our kinematics equations and rewrite them in rotational land? Absolutely, swap out the letters. Everything else behaves exactly the same. How we doing? Long story short, that's a parallel. I want to build it. That's the beginning of the parallel. It'll keep going, but for the moment, I'm going to leave it at that.